Hi, everybody. It's Professor Mitchell. Continuing with Chapter 6, we're talking about 6.4, the central limit theorem. So I have, let's look at the key concept and then I'll tell you what I did. So in this section, we introduce and apply the central limit theorem, which allows us to use a normal distribution for some very meaningful and important applications. So that's not very specific. It actually has to do with samples. Picking samples, taking the mean of those samples, and then looking at how those sample means are distributed. Okay. So for that, I went into a couple of my old PowerPoints from other statistics classes and borrowed a few things that I thought were good. For example, this, I think this really does a good job of kind of illustrating this concept. A bowler records individual game scores and the average for a 3-game series. Records both of those things. Bowlers know that their 3-game averages are less variable than their single game scores. So I don't know how many of you bowl. I enjoy bowling. It's the closest thing to a sport that I enjoy. I'm not any good at it, but I still enjoy it. So if you look at this, these are the individual game scores, and they vary from 110 or so up to 225, okay? So that's quite a bit of variation. Looks like the mean is maybe around, I don't know, 170. So that's pretty good. I think so, at least. But let's say this person bowls 3 games a night, and you look at the average of those 3 games. Those are not going to be as variable. And I want you to think about that. I think that makes sense, right? So it looks like the 3-game averages vary from about 135 up to about 185, okay? So like this 225, that might be their best all-time score. Well, they're not going to do that 3 times in the same night, okay? That 225 probably got averaged with, maybe a 175 and a 150 or something, and it ended up, down in this area, okay? So that's really, believe it or not, the whole idea behind the central limit theorem is that if you take the average of these individual games, that average might come out to about 170. And by the way, that average would be the same no matter whether you average the individual games or average the averages for the night. Okay, it looks like these might average out to about 170. But the standard deviation, which measures variability, is going to be a lot less for this. So when we get into the details, I'm going to show you, okay, how much less. All right, if I know the standard deviation for this distribution, can I figure out the standard deviation for this one? The answer is yes, I can, and I will show you how that works. All right, another example I like, and this is not going to be a typical example. I'm not going to ask you to do anything like this, I don't think, but this one also does a good job of illustrating the central limit theorem. And again, I stole this from another book. So, population consists of 3 housing units where the value of X, which is the number of rooms for rent in each unit, is shown in the illustration. So you have one house that has 2 bedrooms, one house that has 4 bedrooms, one house that has 3. Okay. So choose one house at random and let X be the number of rooms for rent. The first thing I'm going to do is show you the probability distribution for X. This will be a little review from chapter 5, I guess that was. And we're going to find its expected value and variance. Okay, so all things that we talked about how to do in chapter 5. Okay, so the probability distribution is really simple. Since these houses are all equally likely to be chosen, your probability distribution would just look like this. Okay. The probability that X is 2, remember X is the number of rooms for rent. The probability that X is 2 is 1/3. The probability X is 3 is 1/3. The probability X is 4 is 1/3. All right. So now we're going to draw samples of size 2 from that population that has the 2, 3, and 4 bedroom houses with replacement. So I'm going to select a house, write down how many bedrooms does it have. I'm going to put that house back, and then I'm going to pick again, and I'm going to write down how many bedrooms does that house have. Okay. So since I'm doing that with replacement, it's possible to pick the same house twice. Okay. So the new random variable, which I'm going to call x bar, is going to be the mean number of bedrooms in the 2 houses that I picked. Okay. Mean number of bedrooms in the 2 houses that I picked. So I'm going to find that probability distribution. I'm going to write down what are all the possible values of x bar, and then I'm going to write down what's the probability of each one. And then we're going to find the expected value and the variance of that distribution. Okay, so let me show you what that looks like to start with. Here are all of my possible samples. Okay, pick the 2-bedroom house twice, pick the 2-bedroom and then the 3-bedroom, pick the 2-bedroom, then the 4-bedroom, pick the 3-bedroom, then the 2-bedroom, et cetera, et cetera, et cetera. So if I average 2 and 2, I get 2. If I average 2 and 3, I get 2.5. If I average 2 and 4, I get 3. Okay. So these are all of my different possible sample means. Okay. Some of them can only happen one way, like the 2. The only way you can get the 2 is by picking the 2-bedroom twice. Only way to get the 4 is to pick the 4-bedroom twice. But there's like 3 different ways to get 3, right? I could pick the 3-bedroom twice, or I could pick the 2-bedroom and the 4-bedroom, or I could even pick the 4-bedroom and the 2-bedroom, okay? So having a mean of 3, a sample mean of 3, is a lot more likely than a sample mean of 2 or a sample mean of 4, okay? So if you notice, there are 9 outcomes here. There's only one way for 2 to happen. There are 2 ways for 2.5 to happen. There are 3 ways for 3 to happen. So when you do your probability distribution, it looks like this. Okay. The probability that x bar is 2 is 1/9. The probability x bar is 2.5 is 2/9. The probability x bar is 3 is 3/9. Et cetera, et cetera, et cetera. Okay, so here are the probability histograms for my 2 random variables. This one is for x, the original x. This one is for x bar. So the first thing I notice is that x has a uniform distribution, right? Equally likely outcomes. This one already looks a lot more normal, right? You know, if I were to draw a curve over that, it would kind of have that bell shape already. So that's kind of striking. And then on the next slide, here are my calculations for finding the expected value and the variance for both random variables. So over here, and again, we went over this in chapter 5. So here's x equals 2, 3, 4 with probability 1/3 each. I wrote it as a decimal. So here's x times p of x. When I add those together, I get 3, which is the expected value of x. So this 3 comes from here. And then to do the variance, I do x squared times p of x. So this comes from 4 times 0.33. This comes from 9 times 0.33. This comes from 16 times 0.33. I add those together, and then I subtract mu squared. So I was telling the group of students who are sitting in the room with me right now, I'm using the formula that we have talked about, that we talked about in chapter 5. The variance of x is the sum of x squared times p of x minus mu squared. So this number here is the sum of x squared times p of x, and this is what happens after I subtract mu squared. Okay? So I get the variance of x is 0.67. So it's exactly 2/3. Then I go over here and I do the same thing. And look at this, the expected value of x bar is also 3. So that's like what I was saying about the bowling averages. It doesn't matter if you average all of your individual games or you average your 3-game averages. You're going to get the same number, okay? So the expected value of x bar is 3. And now look at what happens to the variance. It does get smaller. All right, I'm not going to, it's the same kinds of calculations we did over here. Here is the variance of x bar after I do all the things I need to do. It's 0.33, okay? That is half of the original variance, okay? So it turns out that that half, the fact that it's half, is because the samples are size 2. If the samples were size 3, this variance would be 1/3 of the original variance. And if the samples were size 5, the variance would be 1/5 of the original. Okay, so the bigger your samples are, the smaller your variance gets. All right, so you've now seen a couple of examples that are sort of getting at this idea. Here it is. The central limits theorem says that for all samples, when you have all samples of the same size n, where n is at least 30, we'll say a little more about that as we go along here, the sampling distribution of x bar can be approximated by a normal distribution. That's why you need the samples to be at least size 30. That makes the sampling distribution normal. If the samples are small, I don't guarantee that this sampling distribution is normal, okay? And the mean and the standard deviation of that sampling distribution are mu, the same as the original mean, but the standard deviation is now sigma divided by the square root of n, okay? The original standard deviation was sigma. So it's important to know, you're going to see coming up here pretty soon some problems that look like problems from 6.2, where we're working in a normal distribution. The difference is that we're going to be dealing with samples instead of individual values. All right, so if you're given a population that has any distribution, it doesn't matter, it can be uniform, it can be what we call bimodal, where the most common scores are the highest and the lowest, and it kind of dips down in the middle. Doesn't matter what the original distribution looks like. Let's say that that population has mean mu and standard deviation sigma. We pick simple random samples. Simple random means that all samples of a certain size are equally likely to be chosen. All right. Now, in order to guarantee that your sampling distribution is normal, you either need the original population to be normal, or you need your samples to be at least size 30. You need one of those two things to be true. Either original population has to be normal, or samples has to be at least size 30. Okay. All right, and so as long as one of those two things is true, then you will get a normal distribution for your sampling distribution. Its mean will be mu, and its standard deviation will be sigma divided by the square root of n. Okay? So the z-score formula, we talked about a z-score formula in 6.2. Let me just show you something here. In 6.2, the z-score formula looked like this. You took x minus mu and divided it by sigma. So what I sometimes like to say is pretty much z-score always has that format. It's a value from your distribution minus the mean of your distribution divided by the standard deviation of your distribution. Okay, so this is just another example of that. The scores from the sampling distribution are sample means. That's why we're calling them X bar. And then I'm subtracting the mean of the sampling distribution, which is just mu. It's the same as the original. That's part of the central limit theorem. And then the standard deviation of that distribution is sigma divided by the square root of n. Okay. And then when you're calculating z-score, especially using this formula, you have to be careful with your calculator. So I think I will bring up my calculator when I do an example of this. Okay. All right. Let's see. Now, if you don't have at least one of those conditions, your original population is not normal and your samples are small, then basically we can't use the methods of this section. Okay, I have to do something else, which we're not going to get into right now. Okay. All right. So considerations. First, check the requirements. Make sure that your original population is normal or your samples are at least size 30. Okay, and then I mentioned this a couple slides ago. Make sure that it's clear, are you working from an individual population, you know, a population of individuals like we did in 6.2, or are you working with a sampling distribution? So usually if you read the problem carefully, you'll either see mention of a sample size or you won't, all right? If you don't see anything about samples, then it's probably a 6.2 problem. But if you see something like samples of size 36 or samples of size 50, then we're probably in a sampling distribution. Okay, but they'll always tell you. All right. So if you're working with individual values, use the old z-score formula from 6.2. If you're working in a sampling distribution, then you need to use this one. Okay. All right. Notation, I think we've talked about the notation, or maybe I only talked about that to the people in the room. All right. So the mean of the sampling distribution, that is sometimes written mu sub x bar. And again, that's the same thing as mu. So I actually don't even use this notation all that much because I just write mu. The two values are the same. However, I do sometimes use this notation because the new standard deviation is not the same as the old standard deviation. It is smaller. Okay, it's sigma divided by the square root of n instead of just sigma. Okay, sigma sub x bar, this thing here, is sometimes called the standard error of the mean. Standard error of the mean, or just sometimes the standard error. Sometimes I call it the standard error. Okay, finally, example. I always look forward to the examples. The elevator in the car rental building at San Francisco International Airport has a placard stating that maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. So if you assume a worst case scenario in which the elevator is filled with 27 adult males, all right, what we're going to be figuring out basically is that likely to be okay? Putting 27 adult males in the elevator. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Okay. So first, we're going to do a little bit of review of section 6.2 by finding the probability that one randomly selected adult male has a weight greater than 148 pounds. Okay. And then we're going to see how does it change when we find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. All right, so again, letter A is what we did in section 6.2. Okay, so first I'm going to draw the picture of my original distribution with a mean of 189. I want to know what's the probability that X is greater than 148. So I mark 148 down here. I shade everything to the right of 148. And now I'm going to convert this to standard normal distribution by finding the z-score for 148. That comes out to negative 1.05. The area to the left of negative 1.05 is 0.1469. Let me just bring that up real quick. Okay, so I'm on the negative side of table A2. I go down to negative 1.0, and then I go over to the column that has the 0.05 on top, which is this column right here. And the area from the table is 0.1469, okay? But remember, that's the area to the left of negative 1.05. So I have to make sure that I subtract that probability from 1. Okay, so this area over here is 0.1469. This area over here is 0.8531. Okay, because the whole entire area adds up to 1. Okay. All right. Now, letter B is similar. It's just that the standard deviation of the sampling distribution is different. Okay. So here's how that goes. We can use the normal distribution if the original population is normally distributed or n is greater than 30. Okay. So I believe they did say that the population of weights of adult males has a normal distribution. Okay. Our samples are almost big enough. They're 27. So that's close. But they did say the original population is normal. Okay. So it's okay to do it the way we're talking about. Because we're now dealing with a distribution of sample means, we have to use these parameters. Mu sub x bar is just the same as mu. It's 189. But the standard deviation is not 39 anymore. It's sigma divided by the square root of n. So my new standard deviation is 39 divided by the square root of 27, which comes out to only 7.51. So the standard deviation of this new distribution is much smaller. Okay. So so see how they've drawn the normal distribution? It's taking up a lot less room on the number line here, and it's just a lot taller. That's what your normal distribution looks like with a smaller standard deviation. It's a lot more squished, this way. Okay. All right, so here is the z-score formula. So I'm going 148 minus 189, and I'm dividing by the new standard deviation. So that's going to come out to negative 41 divided by 7.51, which is negative 5.46. Now I want you to take a moment to appreciate a z-score of negative 5.46. That means that a sample of 27 adult males with a mean weight of 148 would be about 5.5 standard deviations below the mean. That is super, super, super unusual. Remember, we consider anything to be more than 2 standard deviations below the mean is considered unusual. So if you look at table A2, let's bring that up real quick. Table A2 doesn't even have z-scores that low. Look at this. A z-score of negative 3.5 or lower, you just treat the area to the left as 0.0001. 0.0001. Okay. So it's actually less than 0.0001. Okay. But if I treat that as 0.0001, that's the area to the left. The area to the right would be the complement of that. It would be at least 0.9999. Okay. We are quite sure that 27 randomly selected adult males have a mean weight greater than 148 pounds. Okay, so as you can see, I've switched over to my graphing calculator, and that's because I wanted to show you a couple things. First of all, when you're using the new z-score formula, the x bar minus mu divided by sigma over the square root of n, you have to be careful how you enter that in the calculator. Okay. So in this last example, we were doing 148 minus 189, and then we were dividing by 39 divided by square root of 27. Okay, so that 39 divided by square root of 27, that has to go in parentheses, that whole thing. Okay, if you don't put 39 divided by the square root of 27 in parentheses, what it will do is it will divide this thing by 39, and then it will divide the answer by the square root of 27, and that'll give you something different. Okay. All right, so no matter whether you're using a graphing calculator or a scientific calculator, it should look something like this. On my scientific calculator, it looks just a little different with the square root. It gives me a parenthesis, so then I have to close 2 sets of parentheses. Okay, on this one, I just have to do 1. Okay. All right, so there's that, negative 5.46, blah, blah, blah. Okay. Now, the other thing I wanted to show you, in case you're using a graphing calculator, this is specific for graphing calculator, is the graphing calculator will actually tell you what this area is. You don't have to use table A2. So the way that works is you go second variables, which brings up this distributions menu. And finding a normal probability is number 2, normal CDF. So I'm going to bring that up. Now, on some graphing calculators, this will bring up a little menu where you have to put in a lower limit, an upper limit, and the mean and the standard deviation. Mine's a lot simpler than that, but I'll talk to you about what to put if yours looks like that. So on the board behind me, I have the picture for the problem we were just doing. It's going from negative 5.46 all the way off to infinity on this side. So we actually kind of have to trick the calculator. The calculator wants 2 specific numbers, a lower limit and an upper limit. So I'm going to put the lower limit, and then if you don't have an upper limit, you just put some ridiculously big number like this. All right. So negative 5.46 up to, 100 trillion or something. Just put a really big number there. If you're using the kind of graphing calculator that has a menu, just put in 0 for the mean and 1 for the standard deviation, because this is the standard normal distribution. So let's see what this answer looks like. Look at that, 0.999999761. Okay, so that's actually a lot closer to 1 than the answer we got out of the table. I think the answer from the table was just 0.9999. Okay, but it's actually much closer to 1 than that, 0.999999761. So there's, gosh, only about 24 chances in some number of millions that that this group of 27 guys would have a mean weight of 148 pounds or less. That's what it is. Okay, so now just interpreting the results of the last problem. If you think back to letter A, there is a 0.8534 probability that an individual male will weigh more than 148 pounds. And as we have now seen on the graphing calculator, there is a 0.9999998 probability that 27 randomly selected adult males will have a mean weight of more than 148 pounds. Moral of the story, 27 adult males should not get in the elevator. They should take 2 separate trips. All right. Okay, here's something we've seen before, and the next example you're going to see is a really great example of this, and it's also kind of timely because I was just reading about this not too long ago. All right, if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less or significantly greater than what we would typically expect under that assumption, we conclude that the assumption is probably not correct. So the silly example that I've been using for that is if I roll a die 100 times, I expect the number 1 to come up about 16 or 17 times, okay? If the number 1 came up only 5 times, I would say, hey, maybe there's something wrong with this die, all right? Maybe it's weighted funny, or maybe it doesn't have 6 sides or something like that, okay? So here's a great example to illustrate that rule. Suppose that the population of human body temperatures has a mean of 98.6 degrees, as is commonly believed. Also assume that the population standard deviation is 0.62 degrees. If a sample of size 106 is randomly selected, find the probability of getting a mean of 98.2 degrees or lower, okay? So this problem is exactly like letter B of the last problem that we did. So what I would like you to do, if you're watching at home, pause the video and try this problem, and we will come back and compare notes. All right, here we go. So again, we're assuming that the population of human body temperatures has a mean of 98.6 degrees. We weren't given the distribution of the population, but the sample size is 106. So since that's bigger than 30, it doesn't even matter if the original population is normal, okay? All right, so this new distribution of sample means, samples of size 106, is normal with a mean of 98.6 and a standard deviation which is now only 0.0602 something something, okay? So when I draw my picture, looks like this. Here's 98.6, there's 98.2. I'm looking for the probability that the mean body temperature is 98.2 or lower. I was just noticing that they did not color in the part of the distribution that we're trying to find. It's this one here. There's a couple spoilers in this picture. Okay. All right, so now we're going to convert this to a standard normal distribution. We need a z-score for 98.2. So that z-score comes out to negative 6.64. Negative 6.64, okay, which you see here. So this is another one of those ridiculously low z-scores, not even on the table. The table would tell you to just treat this as this area as 0.0001. It's actually a lot less than that. Maybe we'll bring up the calculator. Okay. So yeah, the probability of getting a sample of size 106 with a mean body temperature of 98.2 or less is really, really small. And so what that means, there are two possibilities. There's two possibilities. Either the population mean is 98.6, and I just got a ridiculously small sample. However, what we've just seen is that the probability of that happening is like 0.000, probably a few more zeros, okay? Very, very small. So the more likely scenario is that the population mean is not really 98.6. It's probably lower. And in fact, I was just reading recently that they say that human body temperature has, looks like it's gone down from 98.6. I'm just curious, and also this is a good excuse for me to show you, if you're doing an area to the left, like the one that we're talking about right now, we want to know what's the area to the left of negative 6.64. The way that you would put that into your graphing calculator is like this. You go second variables, normal CDF. And now since there's no lower limit, just put a ridiculously big negative number, like negative 1,000,000,000, comma, and then put your upper limit negative 6.64, okay? So this probability is not 0.0001, it's more like 0.0000010 zeros, and then 1577, all right? Really, really small, 1.577 times 10 to the negative 11. That's like 1 chance in a trillion or something. All right.